Alrighty, electron pairs, okay, and we're going to talk geometry. So we're going to talk about electrons and we're going to talk about shapes. Now what I do want to, this is the formal name of what we're looking at, electron pair geometry, but I want to change something because we used a different term, electron domain. I wish they would call it that, electron domain geometry. Because if you go back, the domains are what we are really looking at. I'll go back just a second. Okay, to get to here. And so what we're going to do is we're going to look at a central atom, okay, and we're going to count the number of domains or places in which electrons have to live. And so we have one here, that is called a lone pair. Okay? And we have two that are single bonds, or a pair of electrons. And then we have an additional one where electrons are there, but it's not just one pair of electrons, it's two pairs, okay, but they're in the same space. So when I am looking for the number of domains, I need to know how many places I need to put electrons around the central atom. In this particular case, the way that it is written, I have 4 spaces for electrons to go. Some of them have more electrons in their space, but I have 4. And it's around the central atom. Okay? So we're here at the electron domain. And so there are 5 possibilities and 5 shapes or geometries that you need to know. All right, looking at my little toys, each of these represents a space where electrons can be. All right, and so this has 2 spaces. Okay, the name of this is linear. Okay, the angle for which between these electron spaces, how far away is this one from this one? 180 degrees, okay? The reasons why these become 180 degrees is because these negative charges want to get as far away from each other as possible. If I go 180 degrees on this side, I'm 180 degrees on that side. If I go any further, I could break my toy. I could get farther away on top, but I'd get closer on the bottom, and so 180 is the best. Okay, this shape, it's a triangle and it's a plane, so it is trigonoplanar. All right, that means I have 3 spaces in which electrons can live. Okay, they could be lone pairs, they could be single bonds, they could be double bonds, triple bonds. What are the angles represented here? Not 109.5. 120. Okay, 120, and that's as far away as they can get. Now this one. How many electron pairs are around it? 4. This shape is tetrahedral. The angle is 109.5 on your FM dial. Okay, and so that's as far apart as you can get those. All right. If you have a central atom and you have a bond, a bond, a bond, a bond, that represents 8 electrons around it. This fulfills octet very well. This is kind of the normal. Okay, all the other ones are, you have to be special to be in them. Okay, they do exist, but this is what we're trying to get to. 8 electrons around the central atom. Okay, and this represents 4 bonds or lone pairs, but this one's kind of the norm. All right, this one's weird. It's a triangle. It's got a pyramid at the top and a pyramid at the bottom. So it is trigonal bi. Okay, and you can pronounce it pyramidal or pyramidal. Both pronunciations are used. And so, okay, the angles, what is represented here? Between here, 120. What about here? 90. What about from this one to the center one to the bottom one? 180. So there are a lot of different angles in this one. This one's a little bit more complicated. We're going to come back to this one and talk about this one a little bit more. 6 electron pairs around it. Okay, what's the angles? 90, top, middle, bottom, 180 is there also. All right. What is his name? Octahedral. Okay, wait. What is his name? Tetrahedral. How many things are there? 4. This is octahedral. How many electron pairs are there? 6. Octa means 8. Oh, what happened? Okay, why this one is 4? It is because it has 1 face, 2 face, 3 faces, 4. That's the 4th. Why is this one 8? 1 face, 2 face, 3 faces, 4, 5, 6, 7 more. There are 8 faces. That's where we get the octa from. It's not the electron pairs, it's the number of faces on the surface of this. That's why it's octahedral. All right. What is this? Trigonal? Planar. This one? Tetrahedral. This one? What are the angles?
180.
There you go. What are the angles? 120 and 90. What's its name? Trigonal, bipyramidal, or bipyramidal. Angles? 90. Angles? 109.5. Name? Linear. Okay, good. All right. 5. You need to know. Okay. Now, when we do and when we solve, knowing the electron pair geometry or the electron domain geometry is important, but that's not really what we want to know. It's a step towards what we really want to know. We want to know what the atom or the molecule really looks like. Now, the electrons are so small we don't see them. So, where lone pairs are, that means you can't see anything because there's not an atom there, but it does influence what the shape is. All right. Now I've got a couple slides, but I'm going to show you with the toys. All right. Linear atoms can only be linear. There are 1, 2, 3 atoms in a linear molecule. Okay. An atom at the end, an atom in the center, and an atom at the end with electrons that are shared between them. Okay. There are 2 possible molecular geometries or real shapes of atoms that come from this particular model. Okay? If you have an atom in the center and an atom on each one of the ends, the molecular geometry is the same as the electron pair, so it's a trigonal planar. But there is one situation in which you get a central atom, an atom here, and then this one's a lone pair. If it's a lone pair, it just takes up space, but it doesn't actually show. So there's a lone pair of electrons here, but there's no atom. What would the shape of this be? Is it straight? No, it's called bent. See? It's not straight, it's bent. So there are 2 shapes possible. Trigonal planar or bent. Okay, trigonal planar has 3 atoms on the outside of the central atom. Bent has 2 atoms and 1 lone pair. Okay? There are 3 shapes that can come from tetrahedral. If you have an atom on each one of the ends, it's tetrahedral. But you could have a molecule that has 1 lone pair and 3 atoms. Okay? It is a little triangle. And it's a little squatty pyramid. So, trigonal, pyramidal. That's what the shape looks like. Okay. There's one more. If you have 2 atoms, a central atom, and 2 lone pairs, take off the lone pairs, what does this look like? It's bent. Ooh, we already saw a bent one before. Are these 2 bents the same? They've got the same name, but how do you distinguish them? What is the angle here? 120. What's the angle here? 109.5. So that's how you distinguish. Even though they're the same name, they are a little bit different. Okay. All right. Here is trigonal bipyramidal. Okay. there are two kinds of bonds in this. Okay? If I think of a globe, there are ones on the North Pole, the South Pole. Okay? And then there are bonds in the middle. What's in the middle of the globe? The equator, right? So these are equatorial bonds. Okay? I don't know what color. Purplish? I have no idea. Periwinkle? Let's go with that. All right? These are equatorial bonds. These are on the axis, the axial bonds. Okay, so they're different. All right, if I had to put lone pairs in here, lone pairs take up a little bit more space. Lone pairs always go on the equatorial because they can get further away. If I put a lone pair here, they're really close to all of these, and so I don't put lone pairs on the top and the bottom, not the axial, but I put them on the equatorials. If by chance I have a central atom and 1, 2, 3, 4, 5 things connected, it will be trigonal bipyramidal. Okay? Options. 1, 2, 3, 4 atoms and 1 lone pair. Okay? I get a shape that looks like this. Okay? Now watch this. What is that? Teeter-totter. Another name for teeter-totter is? Seesaw. Seesaw shape. That's the official name. It's a seesaw. Okay? That is 4 atoms and 1 lone pair. All right? So 3 atoms and 2 lone pairs. Go big. T. It's a T shape.
I got you.
Got it? Got it. Okay. I just don't have it in orange now. Okay? The alternative is 2 atoms and 3 lone pairs. What's its shape? Linear. Okay. So this one can be, this one's most complicated. This one can be trigonal bipyramidal, seesaw, T, or linear. Those are the options. This is the most complicated one. If the central atom has this many electron pairs around it, does it violate octet or no? Yes. So there has to be something special why this one happens. Okay? Doesn't exist a lot. It just exists a lot on homework. Okay? Because we want to give you all the exceptions. Now, you would think that this one's more complicated. There are only 3 shapes from this one. If the other one violated octet, this one really violates octet. It's got a lot of things bound to it. Okay, and so there's some limitations on this one. All right, if you put lone pairs on it, it goes on the top and then the bottom. And so if you've got the atom in 6 things, it's octahedral. If you have 5 things in 1 lone pair, it is a square pyramid, square pyramidal. And then if you have your second lone pair, 1 on top, 1 on bottom, it becomes a square planar. Those are the options. Okay? So those are the options we have. And so here, you can do this. You can say, well, how many bonding pairs and how many non-bonding pairs? Linear becomes linear, or the trigonal planar can become trigonal planar or bent. The molecular geometry for a tetrahedral can be tetrahedral. It has 4 bonding domains, or 3 bonding domains and 1 non-bonding domain becomes trigonal pyramidal. 2 and 2 become bent, different angle. This is the most complicated. Trigonal bipyramidal becomes trigonal bipyramidal if it has 5 bonding domains, 4 bonding, 1 non, seesaw. 3 bonding, 2 non-bonding, T-shaped, and 2 bonding, 3 non-bonding becomes linear. And the last, there are 3 shapes where we have 6 bonding domains, octahedral, 5 and 1 becomes square pyramidal, and 4 and 2 becomes square planar. These are all the possible shapes of all the molecules that we see. Okay? And so, what in the world? Remember, in this, we talk about bonding domains, so multiple bonds are considered 1 bonding domain. And so, when we go about trying to complete a molecular geometry, I'm going to go back just a second. Here are the rules. First off, you've got to draw a correct Lewis structure. If you don't draw a correct Lewis structure at the beginning, everything falls apart. So you got to make sure that's good. How do you check a Lewis structure? What do we use to check to see if your Lewis structure is really, really good? You do what?
Add the electrons up.
Yeah, you add the electrons up and you take the valence electrons minus the ones that you have drawn and you get formal charges, and you want zeros everywhere, if at all possible. If you have an ion, you're going to have charge somewhere. So, but if you have a neutral atom, we want zeros everywhere. That will help you determine if that's the right structure. Then you have to determine the electron pair geometry. This is not hard, so don't make it hard. Count around the central atom how many electron domains there are. Are there 2? Are there 3? Are there 4, 5, or 6? And that will get you one of these 5 shapes. Then the last thing what we have to do is determine, is there an atom there making a bonding pair, or is there non-bonding? Take away all the non-bonding and we'll be left with the true shape of the molecule or the molecular geometry. Okay, so here is a true correct drawing of ozone. All right. Now, ozone is resonance, so we have 2. But if I look at the central atom, the oxygen, I have a single bond. That's 1. I have a non-bonding pair. That's 2. I have a double bond. That's 3. 3 electron pairs, or 3 domains. So I start with this. It starts off as a trigonal planar. Okay? But when I look at that, how many atoms are there? How many things are bound to atoms? Only 2 of them. One is non-bonding, so I take this away. And so the shape of that molecule looks like it's bent. Okay, or the molecular geometry. All right. The molecule 10 with 3 chlorides and a negative charge. If you take a look at that, you have 4 bonding domains. So I start off with a tetrahedral. Okay. And how many non-bonding pairs? I have 1, so I take that off. And so it looks like a little triangle. That's a pyramid, trigonal pyramidal. And so that is what that molecule would look like in real life. Okay. SF4. If you take a look at it, it has 1, 2, 3, 4, 5 bonding pairs with 1 non-bonding pair. And if you look at it this way, it doesn't look like it's shaped, but if you look at it this way, it is the seesaw. And then something really oddball, iodine pentafluoride. And if you look around that, there are 6 bonding domains. And if you take 1 off, because there's 1 non-bonding pair, then it is a square pyramid, square pyramidal. Okay. So, doesn't mean a thing till you do something, right? So, somebody tell me what to do. What's the first thing I need to do?
Add electrons.
Add electrons. Okay, so carbon. How many valence electrons from carbon? 4. How many from oxygen? 6. And 6 times 2, get out your iPhones. 12. Good. 12 plus 4 is 16. Great. All right. What's the central atom? Carbon. Make 1 bond to each of the elements on the outside. How many electrons did I use at that step? 4. I have 12 left. Next step. What was that? Fulfill octet for oxygens. How many does each oxygen need? They need how many more? 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I just used 12 electrons, and I have 0 left. All right. What's my last step? Do any electrons go on to the central atom? Nope, don't got any. Does the central atom have octet? How many electrons are around carbon? 4. Ooh. If I take one of those and make a double bond, okay, I take it and put it over here. That doesn't get me up there far enough, and so I'm going to do another one, and so I'll end up with this. Oxygen, double bonded to carbon, double bonded to carbon. And if I count octet for each one of those, I didn't change oxygens. I still have 8 around them. 4 represented here as the electron, as the bonds, plus 2, 4 more. 4 plus 4 is 8. Carbon now has 2, 4, 6, 8. And the other oxygen is the same. Is it a good molecule? I need to check formal charge. Each oxygen brings in 6 minus the way I drew it. 1, 2, 3, 4, and then 1 for each bond. 1, 2. No. Okay. That's 6. 6 minus 6 is 0. So that one's 0 also. Carbon brought in 4, assigned 1 from each bond. I have 4 bonds. 4 minus 4 is 0. I've got a perfectly good molecule. Alrighty. Good. That was just the beginning. I haven't even started yet, right? How many domains are around the central atom? 2. Are there any non-bonding pairs? No. So, what is the name of the electron pair geometry? Linear. What is the shape? Linear. Linear, linear. Good. All right, I'm going to skip the next one and go down to NF4. Okay, NF4. Stop it. Nitrogen brings in how many? How many electrons? How many valence? 5. How many does fluorine bring in? 7. Times 4, 28. All right, we got an issue that I forgot to tell you. This is positive. Oh, that's not exactly what I wanted to do. Let me take this back. I'm going to go back and I'm going to change it all. Oh, too bad. I have an eraser. Okay. I'm going to do this. NF3. That's what I really wanted. Okay. You said we had... Stop it. 5 for nitrogen. 7 for fluorine. Fluorine, 7 times 3 is 21. 26 electrons. Nitrogen, central atom. 1 bond to fluorine each. Used 6. Have 20 left. Fulfill octet on every atom on the outside. 1, 2, 3, 4, 5, 6. 1, 2. Stop it. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I've used 18 electrons at that moment in time. I have 2 left. Okay. Where do those last 2 electrons go? On the nitrogen, the central atom. I need to check nitrogen. Does nitrogen have octet? Yes. 2 lone pairs, 2 from the lone pairs and 6 from the bonding pairs around it. Check formal charge. Each fluorine has 7. I account 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0 for each of the fluorines. Good night. Nitrogen brought in 5 minus the way that I drew it. 1, 2, 3, 4, 5. And that would be 0. So that's a good. All right. Just started. Nitrogen. How many domains are around the nitrogen? 3, 4, 6, 4. Okay, started with 4. How many of them are non-bonding pairs of the 4? 1. Take that away. What is the shape? It is a triangle and a little pyramid, so it's trigonal pyramidal. Okay? All right. So it is tetrahedral for the electron pair, but trigonal pyramidal for the molecular geometry. All right, so as we approach these, all right, I want you to be able to identify the molecular geometry. Now, I'll be really, on the homework, we can give you just one question. What is the molecular geometry? If I just ask you what the molecular geometry is, does that lessen your work at all? No, it just lessens mine. I don't have to ask you for each one of those things. But you have to do all of them. So, do CCl4 for me. One thing as you approach these problems, any one step is not complicated. The problem with this is there are a lot of steps, and making sure that you account for each thing in each step. Okay, and so for CCl4, my Lewis structure would look like this. Okay, and if I look at that, there are around the central atom carbon with 4 pairs. That means it's a tetrahedral. And when I look at it, are there any non-bonding pairs? No, so it's a tetrahedral. So tetrahedral, tetrahedral. Okay. Carbon tetrachloride. All right, I've already taught you the bond angles. Okay, and this is where we point out that the axial, the ones that are above and below, are 90 degrees away from the equatorial, and the equatorials are 120 degrees away from each other. And non-bonding pairs will always go into the equatorials. Octahedral, 90 degrees from any one or any 3 of them. Okay. Here's the deal with angles. If you have to estimate and tell me what the angle is, like on homework, you use the default angles, okay? The main set of angles. But here's the deal. Is real life perfect? No, real life is never perfect, okay? Now, here's the deal. When you have bonding pairs of electrons between two atoms, that means they're held on one side by one atom and held on the other side by the other atom, and they keep the electrons in between the atoms and kind of wrestle them and keep them contained, okay? They don't take up as much space if they're being held on both sides. But the non-bonding pairs that are held on by one side, on the other are kind of free. So they actually, in real life, take up a little bit more space, okay? And so the non-bonding pairs can actually take up more space. And so if I take a look at this molecule, a tetrahedral, if I have 4 bonding pairs, they're all the same size. So the angles would be 109.5, just like I would predict them to be. Like that last one that you did, carbon tetrachloride, 109.5. Okay. But if by chance you have a molecule and this one's a lone pair, what happens is the lone pair is huge. And remember, these things try to repel from the electrons. And if I've got a big one up here, what happens is these all get bent in just a little bit. So their angles aren't perfectly 109.5, they're a little bit less, okay? Now, I will never ask you to predict what that little bit less is, okay? But I can ask you, are they perfectly 109? No, they're not. 109.5? No, they're not. They're a little bit less. And so an example would be ammonia. The angles go from 109.5 to 107. The reason is this lone pair is just taking a little bit more space. What would happen if you pick 2 lone pairs? Well, you've got 2 things that are taking lots of space. So what happens is these get bent down even more. And so the bond angle is even less. Would I make you predict what that number is? Absolutely not. Because it is different for every molecule. In terms of water, it would be 104.5. But I just memorized that because I've seen it for 20 years, right? It's not something that you would know, okay? So if by chance you drew out water and you saw this, and it asked you, what are the angles? You say 109.5, because that's what you could predict. But if I ask a question, is it really 109.5? Is it smaller or larger? You can answer, it is smaller, but you will never be asked for a numerical value of what it really is. Okay? So, lone pairs take up more space. When we count electron domains, we count lone pairs, right? We count single bonds. We also count double bonds and triple bonds. Do you think the double bond is bigger than the single bond? Yeah, it takes up more volume. And so, if you look at this molecule here, there are 3 bonding domains, right? 3 bonding domains gives me a electron pair geometry of trigonal planar. You would predict, if on a question or the exam, that these should be 120, okay? But in this case, you have 1 double bond. So this is a little bit bigger, this one. Just takes up more space because there's 4 electrons rather than just 2. So these get squished down just a little bit. So the bond angle between chlorine, carbon, chlorine is smaller than the bond angle between oxygen, carbon, chlorine. Okay? And so if you had to predict it, you would say 120 if you had to type in the angle. But I could give a question. Which angle is larger? Chlorine, carbon, chlorine, or oxygen, carbon, chlorine? You would know the oxygen, carbon, chlorine is larger because that double bond takes up more space. If there was a triple bond in there, that would take up even more space. Okay? And so, life is not perfect, but if you have to predict, you predict one of the default angles. I will never ask you what the real, an exception is. I won't ask you for a numerical value, but I might ask you which one's bigger, which one's smaller. I could do that. Okay. Oh, booger now. Look at this thing. Here's a molecule. What is the central atom?
Carbon.
That is correct, but only a third correct. It could be carbon. That would be 2 carbons would be 2/3 correct. And an oxygen. There are 3 separate central atoms that you have to deal with individually, okay, to know what the shape is. And so there's carbon number 1, there's carbon number 2, and there's oxygen, that is 3. And so if I looked at this and I looked at carbon number 1, how many electron domains are around that carbon number 1? It would be 4, which would be what shape? Tetrahedral. So it would look like this. That carbon number 1 looks like this. The next one, carbon number 2, how many electron domains are there? There are 3 electron domains. That would look like this right here. Okay? And so this is carbon 1, this is carbon 2. Okay? So that's carbon 1 and carbon 2. This is what it looks like in 3-dimensional space. And then the next one would be next around the oxygen. There are 4, right? So I start with the tetrahedral, right? But how many lone pairs do I have? You have 2 electron pairs. So it becomes what shape? Starts with tetrahedral, take off 2, it's bent, right? And so this is not perfect, but it's kind of like this. It would look like this. So you would have a shape that has a tetrahedral for one of them, a trigonal planar for the next, and the last one would be bent, although the angle's a little off on this one. And this is what this molecule in real life would be floating around, twisting around, and it looks like this. Okay? And this particular molecule right here, you take it in a bottle and you shake it on your fish and chips. Because this is acidic acid or vinegar. Okay? This is what vinegar really looks like in 3 dimensions. Okay? Floating around, twisting around, and the shape is all moving. Because it's in the liquid and it's moving around and it's tumbling and it becomes pretty complex about what's happening. All right, so here's the deal. What did I show you? What did I want out of this for you? Molecules get big. But to know the shapes of molecules, what we do is we look at each individual central atom and we determine what the shape is around each one of those. So I might give you problems that have central atoms, lots of them, in a big molecule, and I'll identify which one I want you to deal with at any one time. Okay? And so this particular one I did. So here is a very an example of what I like to do. Okay, so eye drops for dry eyes contain a water-soluble polymer called polyvinyl alcohol. Okay, and so the vinyl alcohol is shown here. What is the approximate value for the bond angles? Oh, all right. In hydrogen, oxygen, carbon, and then oxygen, carbon, and carbon. Okay. So let's look at this. We first want to look at the one that is hydrogen, oxygen, and carbon. We want to look at that one. So this bond right there. If I look at that bond right there, which one is the central atom? Oxygen. Okay. So now that I've identified the central atom, then what electron pair domain am I dealing with? A what? A tetrahedral. Okay. So tetrahedral is this. All right. And if I look at that for real, how many non-bonding pairs do I have? 2. Okay. So the angle in CHEM-111 what would you write? What would it be? It would be bent, but what angle value would you say? 109.5. In real life, is it bigger or is it less than 109.5? In real life. Less, because these lone pairs take up more space. That means these get bent down, and so that angle is less. Okay? The numerical value, I'm not actually going to ask you for that on the exam. I just want you to understand it's less. Okay, that's not the only thing am I asking. Okay? I'm asking from oxygen to the carbon to the carbon. What is the central atom in this? A carbon, and one of them, so I'm going to call it carbon number 1. All right, how many electron domains are around that one? 3. And when I have 3, what is my shape? Trigonal planar. What would be the angles around this? 120. Do I have any non-bonding pairs? No. So it looks like this, right? All right. What would the approximate angle be? Well, let's see. It's 120, but would it be perfectly 120? No. It would be just slightly less, because why? Double bond. Okay? And so I could do some sort of questions like that. It looks big, it looks more complicated, but what you do is you have to identify which central atom you're looking at, and I could give you a huge one and put a star next to one of them. You just look at the star one. Okay? Don't let all the other stuff confuse you. Okay, polarity. This is the last concept. Ooh, you're going to have to tell me if a bond is polar. How do you determine if a bond is polar? Which trend are we looking at? Electronegativity. Okay, and electronegativity, okay, basically is this. If you have them very far apart in the chart, they're very polar. Too far apart, the electron actually jumps and becomes ionic. Remember I told you that? That if you have too large of an electronegativity, we actually take one of the electrons, one gives. But if they're really close, okay, they're still sharing electrons, right? But it's not equal sharing. All right. What are the only atoms that actually have pure covalent equal sharing? Diatomics, yes. Because each one has the exact same electronegativity, the electrons will be right in the middle. There's only 7 of those, right? And then there's sulfur found as S8. Those bonds would be absolutely nonpolar. There's one defined, carbon to hydrogen. It acts nonpolar, and we define that as nonpolar. Every other molecular compound is a little bit polar. One of the 2 is a little bit more electronegative. One of the 2 will be tiny bit negative. One will be a tiny bit positive. This is an important concept, not for just this chapter, but next chapter. Or this, we're going to have a question on this exam about polarity, bond polarity. We're going to look at differences in electronegativity. We're going to talk about polarity here in this next unit, chapter 6, so that's test number 3. And then way in test number 4, we're going to talk about polarity in a whole different terms about how molecules interact amongst each other. So this is a key item, something that you really need to understand. So bonds, almost every single bond in almost every single molecule that you draw a Lewis structure are polar. Okay? Almost every bond is polar. But that doesn't necessarily mean that the molecule is polar. How can you have polar bonds, but the molecule be nonpolar? That sounds like I'm lying to you, okay? In terms of polarity, it's almost like tug of war, okay? Between each atoms, there's a pull or a tug of war on the electron pairs, okay? But in a molecule, there is also a tug of war. Okay? So if I have a central atom and I have this atom and this atom, and it is electronegative this way and electronegative that way, and they're both pulling at the same distance, then what happens is it balances each other out. And so the molecule becomes nonpolar even though it has polar bonds. It is rare that that happens, but it can happen. Most of the time, if you have a polar bond somewhere, the molecule will be all over polar. But every so often, you'll have polar bonds, and they cancel each other out. So this one can be canceled each other. That one can cancel each other out. This one can cancel each other out. What do you have to have poles to cancel each other out? Every bond has to be pulling at the same strength in all three directions. That means this atom, and this atom all have to be the same. And if they're pulling or they're pushing, okay, depending upon which way, they all have to be pulling at the same strength. If they're all pulling at the same strength on all three sides, it is nonpolar. Polar bonds, nonpolar molecule. No, lone pairs don't pull at all. Can this ever cancel each other out? This shape. If I have no pull on the top and I have pulls on the bottom, there's no way to cancel this. If you have polar bonds in this shape, it will always be polar, because I would need 3 pulls for it to cancel. I only have 2 pulls. It can never be nonpolar. Could this one be nonpolar by chance? Yes. If all 4 pull at the same strength, nonpolar, even though polar bonds. Could this one ever be? If you've got polar bonds, this one can't cancel each other out. Same with this. If you have any polar bonds, there's no way to cancel each other out. To get more complicated up. Can this one be nonpolar? You have to have pulls in all directions, but yeah, it can. Can this one ever be? Nope. Could this one ever be? Mm-hmm. Could this one? Yes. This one could. Back and forth. Could this one ever be nonpolar? Wait. Oh, this one. Yes. If you have 6 pulls in all directions. Could this one ever be? No. You could have pulls this way, but this one's always going to get you. What about this one? You could have pulls and cancel each other out, and as long as you have lone pairs on the top and bottom with no pulls, this one could possibly be. Okay? So, here, if I really want to be nasty, I just say, is the molecule polar? What do you have to do? Lewis structure, electron domain, molecular. Think about if the bonds are polar or not, and then think about if they're canceling out. I love those type of questions. One question, 80 parts, right?